Capacitors are defined by their ability to hold charge. Specifically, their ability to hold charge per voltage. We'll note that current is the change of charge over time. So let's put a capacitor in a DC circuit with a resistor. From Kirchhoff's laws, we can see that the voltage applied is equal to the voltage across the capacitor, C times Q, plus voltage across the resistor, I times R. If we do a little bit of calculus on this equation, we find that the current through the circuit is an exponential decay with a time constant of RC. So when we first connect this circuit, Vs is going to drive current as if the capacitor was a short circuit. Our initial current will be Vs over R. That current, though, is going to build up charge on the capacitor. That charge on the capacitor is going to build up its own voltage and slow down the current. And eventually that current will decay to zero as the voltage across the capacitor rises to Vs. If we then disconnect Vs and short circuit those terminals, the energy stored on the capacitor and its voltage are going to discharge back through the resistor. The current is still going to follow this exponential decay, of course with the current going in the opposite direction, and the result is that the voltage across the capacitor is going to be an exponential decay. We can show that by displaying this circuit on an oscilloscope. We're going to choose an R of 1 kiloohm and a C of 100 nanofarads. So the RC time is 100 microseconds. On screen here, the yellow is the applied Vs, and the blue is the voltage across the capacitor. We see that when we apply the voltage, there is a 1 minus exponential decay for the capacitor to rise to that voltage. Now when we discharge that voltage, there's a simple exponential decay on the capacitor. And we can see it takes about 100 microseconds, the RC time, for an E folding. That is, for the voltage to drop to about a third of its initial value.